Hi, my name is Ana Karen Lozano Joan. My ID number is A0128-5982, and this is my video for the second coursework.
Okay, so in this video, I'm going to explain the solution for modeling a simple mobile robot in RVs using the TF and the RVs markers. This node publishes a dynamic transform from the world to baselink so the robot moves, and also publish many static transform from the baselink to each part of the robot, like the chassis, the wheels, and the caster. And then it publishes the marker so we can see all of these parts that I just mentioned in the RVs. So I'm going to start first with the Python code. We start with this line, just saying that we're going to run this file using Python. Then we start importing these libraries. And then we have our helper function makeTF. So basically, this function creates and returns a transform stamped message. So I use it to avoid repeating the same message set up many times. Well, in here, I create an empty transform message. Then I set the timestamp, which is basically if a stamp is passed in, I use it, and otherwise I will use the current rust time. Then we set the parent reference, the parent reference frame name, and also the child frame name. Then in here, these lines set the translation in meters. Then we have the quaternion, which is basically that the TF uses a quaternion, so I convert the roll, the pitch, and the yaw into a quaternion. And then these lines copy the quaternion values into that TF message. And well, finally, I just return the fully built transform. Then we have this shutdown function that basically, well, this function will run when the node is shutting down, and it just prints a message on the terminal. And on a real robot, this could send a stop command. Then we have our main code. This means the code below will run only when the script is executed directly. So we start initializing the ROS node. The node name is robot. Then we have the rate. This sets the loop frequency to 30 Hertz. So I publish updates 30 times per second. Then the shutdown registers my stop function. So ROS calls it when the node exits. And then we start with the parameters. The radius path. Basically, I read a private parameter called radius path that controls the radius of the circle path. And if it's not provided, it will be set default to 1 meter. Then we have the omega parameter, which is basically reading the angular speed omega in radians per second. Then we have the base height, that is an offset to lift the chassis above the base frame. Then the chassis wheel and caster geometry parameters. The chassis L, W, and H define the chassis size. Then the wheel R and T define the wheel radius and thickness. And then the caster R defines the caster radius. And well, these parameters make the robot easy to resize without having to edit the logic. Then we start computing the relative position of the robot parts. These sets the wheels on the left and right sides, half the chassis with plus half the wheel thickness, and then these will set the wheels centered in the X relative to baselink, and these will help us to center also the wheels on one radius above the ground. Then we have the caster position. This basically centers the caster towards the back. This means that it's centered, and this means that it will be touching the ground. And then we have the chassis position, which is basically placing the chassis above the base link. And then we have the broadcasters. This broadcaster is used for the moving transform world to base link, and this is used for the fixed transforms from the base link to the robot parts. Then we start publishing the static transforms. These will be published once. So we start by creating the list of the static transforms, and well, this is each line corresponds to the base link to the chassis, base link to the wheel on the left, on the right, and the base link to the caster. And now we send all the static transforms at once, because these won't change over time. So this basically helps us to define the robot structure. So once the static tree exists, moving the base link will move the whole robot. Then we have our marker publisher. We start by creating the publisher that will publish the marker message on the topic robot marker. And then I store the wheel rotation angle. And well, this is only for the visual animation. And this prints a message once everything is initialized. And then we have our shutdown function, which is like our main loop. And this will run until ROS shuts down. And well, we start by getting the current time in seconds. Then we have the dynamic TF. The first two equations for x and y create the circular motion around the origin. Then I also rotate the robot as it moves, so it faces along the tangent direction. And then with these lines, I create the transform from the world to the base link, and I broadcast the dynamic transform every loop. Then we have update wheel spin. This line helps us to estimate the linear speed for the circular motion, because b equals radius times angular speed. Then this is a time step for 30 Hertz. Then we have the wheel angle, the speed in b divided by wheel radius, and this keeps the angle bounded, so it doesn't grow forever. Then we publish the chassis marker. We start by creating the marker message, and then we attach the marker to the chassis frame. Then the namespace and ID uniquely identify this marker, so the RBs updates correctly. And well, then this marker is a cube for the chassis. Then we have the we set the chassis dimensions and the color and transparency. And finally, with this line, we are just publishing our chassis marker. Then we have the wheels marker. So I created two markers, one for each wheel frame. And this part is making it a cylinder. Then we have, well, the frame ID, it will attach it to the wheel left or right. We also have the scale, which is basically also setting the wheel diameter and thickness. And then we have the wheel, the alignment, like the orientation. The first part, the Q line, rotates the cylinder so it looks like a wheel. Then the spin rotates it to simulate the spinning. And the quaternion multiply combines both rotations. And yeah, so we're setting like the spin and the line. And then we have our orientation that assigns the quaternion. And same as the other, we are just publishing our marker. And then finally, we have the caster marker. So it's basically the same. We're just setting it to a sphere. We are using the frame ID caster to attach it to the caster frame. We use the scale to set the diameter based on the caster radius. In here we are setting the color, and we are publishing it. And then the rate sleep will keep the loop running at 30 Hertz. And this helps us to prevent an error message when the node is like stopped normally. And now I'm gonna explain the launch file. Well, first, the launch tag will start the launch configuration. The first node runs the Python node from the simple mobile robot package, and inside that node we have the parameters like the radius pad, the omega, and the rate. That is actually hard-coded. And we also have the RBs just to open it automatically when we run the ROS launch. Okay, so now we're gonna start with the terminals. In here we're gonna put that on ROS core. Then we're gonna open another terminal. And in here we're gonna have make, and then we're gonna source Okay, so we have our RBs. In here we're gonna select world, and we're gonna add the fixed frames, we're gonna add TF, and we are gonna add the marker. And we're gonna set this to robot marker. So as we can see in here, we have our robot rotating around our world, and I hope you can see like you can see in there that it has like the wheels and everything. I just don't know how to zoom in the RBs, so I haven't been able to zoom it, but here it is, the result.